All right. Hello, everybody. Thank you for joining us. We are going to get started in just a minute. Let me bring out the presentation for everybody. So we have that. Um, and yeah, we'll get going in just a minute. Thanks everybody for tuning in. We really appreciate your time today. All right, here we go. All right, we're going to get started about 2 minutes after the hour. We're going to let folks come in to the Zoom. And we're broad streaming, we're live streaming on a few other places as well, including, I believe, YouTube and LinkedIn. So wherever you're tuning in from, welcome, welcome. Excited to have you here. And for those that are just hopping on right now, we're going to be starting our broadcast here about 2 minutes after the top of the hour. Um, so yeah, we'll be back with you right when we're ready to go. We got one more minute till the 2 minute after minute, and then we'll get started. So thanks everybody for joining. Really appreciate it. Excited to have you all here and share some cool stuff that we got prepared. Okay, I think we are ready to go. All right, well, thanks everybody for tuning in. I'm really excited everybody's here. My name is Ben Pruden. I'm joined by Daniel Smith. We'll do intros in a second. But we're going to be going through a bit of an overview of Wherobots and Apache Sedona in the context of folks that are mapping and building and maintaining maps. So this is one of the core things that we hear very frequently about when we're working with users of Apache Sedona and customers of Wherobots is they oftentimes want to build these really high definition and oftentimes even super definition maps of the world. And so we're going to be walking through how you can go about doing that using Wherobots and Sedona. So I'll go ahead and get started. Um, I'll just kind of go through. This is our agenda for today. Obviously, we're welcoming you. Welcome everybody. We're going to be talking a little bit about, where we see the world headed and the need of closing the gap between AI and LLMs and the physical world. Um, we're going to be talking about the lakehouse architecture for map making teams. Daniel's going to jump into a really cool example, workflow demo of how you go about applying Wherobots and Sedona to solve this type of use case, together with a number of other open source technologies that we're actively working on, Apache Iceberg in particular, and Parquet for data formats. Um, we'll go into a little bit of a case study. So we'll talk about how the team at Amazon Last Mile actively used Sedona to build their digital representation of the physical world and what that looks like and how they go about doing that. And then, of course, we'll close out with some thoughts and some Q&A. And then as we're going here, we've got some polls that we're going to launch as well because we're really curious about your feedback. So I'll be having those come up as well. But like I said, I'm Ben. I lead the go-to-market team here at Wherobots. Daniel, you want to introduce yourself?
Yep. Folks, my name is Daniel Smith. I am one of the senior solutions architects here at Wherobots. Thank you, Ben.
Yeah, of course. Awesome. Okay, so let me just start with three takeaways before we get into the meat of it. So, we here at Whereabouts are really focused on enabling organizations of all kinds to uh, handle spatial data at really planetary scale and enable that analysis of the physical world in a way that previously maybe either been too costly for you or too difficult to do in a really efficient and modern cloud, native platform. We're building data and we're building spatial data capabilities into the modern data stack, into the lakehouse architecture. And so we're going to be talking through what that looks like today in terms of where and how we see the lakehouse really embracing and where we're really driving things with the lakehouse and embracing the modern data stack for geospatial. And then finally, ultimately, for those of you that are interested or considering or thinking about working with Whereabouts, we're here to help you advance your mission of handling, dealing with, processing, and managing spatial data and non-spatial data together to better understand and operationalize your business and what or your organization in whatever way possible. All right, so we're going to start with a poll. I'm curious what folks have to say, so let me get that one up and running. So the question is, um, how do you use mobility data today? And so I just launched that poll. You can respond to that poll. And then I believe this has to be for folks that are on the Zoom. If you're not on Zoom, then you're welcome to incorporate your results or share your feedback. Um, so, all right, we've got a lot of folks responding, got 50, almost 50% participation. Looks like a lot of folks are not yet doing stuff with mobility data, but it looks like a good portion of you are using it for map making, which is sort of our core use case today. So that's really cool. Yeah, we got 74% participation, 76% participation. And so if you're not on the webinar, I think you can actually use this little QR code here to respond to the poll as well. So I'll share that for a second. If there's anybody else wants to hop in. All right, let's see what the results are. I'll share those results right now. So you can see we had uh, targeted advertising, about one respondent. Map making is really the majority of the folks that are using the data. 11 out of the folks that are participating, uh, 31%. Uh, Insurance and driving risk, 6%. Public safety, 6%. And then a good portion of you are not doing stuff with mobility data today, and that's fine. Totally understand. All right, so let me go back to the slideshow view. Um, Dan, you still seeing that come through okay? Got a lot of switching of screens. Good. All right. So let's talk just briefly about Sedona. Sedona is used by over 20,000 organizations to do large-scale spatial analytics on Spark or other distributed computing architectures. It's really grown really quickly over the last almost 7 years, 8 years now since it was originated back in, early mid 2017 or 2015, 16, 17 time period. And that's really because of its broad support of spatial SQL, Python, the ability to read and bring in lots of different data types. One of the hardest things that we've done with Sedona, that our team that manages Sedona has done, is being able to read over 80 or not, I can't remember exactly how many, but a large number of different spatial data formats and then convert those into modern data types. So for example, being able to write out to Parquet or GeoParquet and do all sorts of raster data management as well. So being able to read in cogs and then push those out as well. Then do lots of different spatial joins. There's over 300 different 200 vector operations and about another 100 raster operations that you can do with Sedona. That really helps to speed up your data processing and efficiency, as well as just give you a whole workbench of capabilities on top of Spark or other distributed computing systems. It's used, like I said, by over 20,000 organizations. We've seen over 50 million downloads. We're seeing, continuous growth year over year, over 200% growth, over 140 contributors. And I'll talk specifically, we'll share the case study for Amazon, the last mile team specifically at the end here today. All right. So one of the problems that we are addressing as a company is when you're interacting with AI systems today, like a ChatGPT or other sort of large language model, you want to ask questions about what's going on with the physical world. You want to understand how the physical world is changing and what you should be doing as it relates to your business. But oftentimes the models that are out there, they're pulling in other internet data. They're pulling in text data. They're pulling in other sources of information, but they're not actually referencing the true information about the physical world. And that's a gap. So what ends up happening is that as when you ask questions about the physical world, oftentimes the LLMs that you're working with will kind of hallucinate. They'll kind of make up the results and give you answers that are not fully there. So that's kind of one of the core issues that we see is like, how do we help connect your data and the world's data about what's happening on the planet today to large language models and make them so that you can communicate and talk with large language models in the context of the data that you've got and the data that you want to process about your business. So our mission as a company, really what we're focusing on is making spatial data easy to utilize across any number of different systems. The core thing that we see at the base layer of the problem is that processing spatial data historically is an extremely expensive exercise, extremely compute intensive, and it also requires a large degree of customizations of architectures. So we want to simplify and reduce those costs, and that's really what we are focused on, reducing those costs for companies to handle that spatial data, improving your overall developer experience and simplifying that developer experience. You have a great breadth of functions to run and analyze the physical world. To grow the Apache Sedona community, we're the contributors and maintainers of Sedona. We really want to continue to see that grow, and so we're pushing that forward. And then finally, what I was speaking about just now, enabling AI for the physical world and really delivering the models that want to consume this type of information, the embeddings and the data that they need to interact with data about the physical world in ways that previously was not really possible. So when you're working with Wherobots as a technology, as a team, there's really four core benefits that we see again and again with our customers and with our users. First, everything that we're doing, everything that we have in our cloud service is 100% compatible with our open source and other open source projects. We are an open core company. Everything we do enables that you to, for whatever reason, if you don't like us, which hopefully won't be the case, you can always, switch back to an open architecture. You can use Sedona, which we will continue to maintain and drive forward. But we enable you to use our systems in a way that is very much compatible with our open source. But the other thing is that when you're using our cloud service, it's the fastest, the most performant system out there for processing very large scale spatial data or very in-depth spatial data, high density spatial data. It's anywhere between 5x to 20x faster than most other distributed computing architectures. And so that's really what we really want to see, is that enables a great deal of productivity for developers, for data scientists, for data engineers, working with both vector, raster, and then combining that data with the tabular data that you have in your business, right? So not just having spatial data sit off on its own little silo over here, but actually making it core to the other type of data and analytics and AI that you want to have as questions. And then finally, we're on AWS. We're an AWS partner today. When you work with Wherobots, you can spin things up as a serverless instance, and it just runs while you're processing the data or while you're running in a notebook type UI. And then when you're done, you can destroy your workload, it spins back down, and that's it. So you don't have to worry about having these compute resources that are sitting off constantly running. You can just consume it when you need it and then kill it when you don't, and you're only paying for what you use when you're using it. And then just lastly, around the performance parts, these are some benchmarks that we've run. We're actually actively working on a big benchmarking project right now, so we'll have more news to share there in the coming weeks. But there's kind of this is really a view of when you work with Wherobots DB, how much faster it is than other distributed computing systems that handle spatial data well, including, for example, using our open source Apache Sedona in a Spark or on a Databricks type of deployment, or with BigQuery or Snowflake. So again, when you're using Wherobots, you get the fastest, the most performant view. And that looks like we got somebody who's raising their hand. We will take questions at the end, so feel free to keep that, or you can ask it in the Q&A box. Happy to respond to it that way. All right, so we got another poll. I'm going to launch this poll really quick. So let me just get that going. Share polls and quizzes. Okay. Let me go back, sorry. All right, number poll two. So how are you processing geospatial data today? There's lots of different ways to do it. We understand that. We appreciate that. So, are you using Postgres or PostGIS? Are you using GeoPandas or GDAL or Dask? Are you using BigQuery? Are you using another Sedona on Spark type deployment? Uh-oh, did I launch the wrong poll? I did. Oh no, I launched the poll about inference on satellite imagery. All right, well, let's do that one instead. We're doing a different poll. We'll come back to this poll. So what challenges do you have running inference on satellite imagery today? So let me get that QR code. So that'll be another thing that we'll be talking about. We give you the ability to run and have inference on satellite imagery. So what challenges do you have when you're doing this type of inference? And what do you see as sort of the problems that you have with that? Cool. Good responses. A bunch of you saying that your current workflow doesn't scale. A number of other folks saying it's too hard to productionize. Um, or you're some good portion of you, actually, not surprising, are not doing it yet. Again, that's also something that we see. It's something that maybe you want to do, but you're not there yet. Um, good. Cool. You're currently working on drone images. Well, that's fair, actually. So you can include that as well. So are you running inference on those drone imagery? We actually support both inference on satellite or drone imagery. So you can do that in Wherobots too if you're using a drone imagery. Cool. All right, let me in that poll. I'm going to go ahead and got a good chunk of responses there. We'll share those results back with everybody. So yeah, good portion of folks are complaining with issues around their current workflows don't scale. Another good portion say it's hard to productionize. It's about 29 and 20%, 43%, almost half are saying, I mean, you're not running these inferences at all on satellite imagery. And then, yeah, thank you for that comment as well about what you're currently doing with drone imagery. All right, let me stop sharing that one. All right, since I missed my geospatial data processing question, I'm going to go ahead and launch that one too. So let's do one other poll really quick. And I'll get that QR code going too. So how are you doing your spatial data processing right now? Is the second question. Are you using Postgres, PostGIS, GeoPandas, GDAL, Dask, BigQuery, Sedona on Spark? Let's see what people have to say. If you're thinking about some of you thinking about using Wherobots, thank you for thinking about using Wherobots. That's awesome. A lot of folks using Postgres, PostGIS for geoprocessing as well as GeoPandas. This is not surprising. This is something that we have seen and heard from many other folks. And we totally get it. It's great stuff. Cool. All right, let's get we're going to end the poll now. I feel like I got a good chunk of responses. Thank you. Also share those results as well. So you can see 37% said you're using Postgres or Post GIS for your data processing, spatial GeoPandas. There's 65% of you using GeoPandas. GDAL 40%, Dask 5, BigQuery 7, Sedona and Spark 33%. So a good chunk of you all using Sedona. Thank you. And definitely a good chunk of you are also thinking about using Wherobots. This is I believe this was a multi-select question, so you can, and a few of you are selecting something else. So that's cool. Awesome. All right, well, let's go back to the presentation. That was really fun. I enjoyed those. That was really helpful feedback for everybody. Let me go back to presentation mode. Okay, cool. Went through 2 fire rounds of poll questions. So let's just talk for a minute about how Wherobots and the Lakehouse engine works. And then shortly after that, we'll go a couple more details and then we'll jump into Daniel's demo. So when you're working with Wherobots and when you're working with the Lakehouse for spatial data that we are supporting and delivering, You've got a lot of different data sets that you have. Typically, they're in cloud storage or and some, other database that you're dealing with. So we can connect directly where that data sits. We connect it directly into it if it's in Amazon S3 and simple storage service, or if it's in Postgres or in other systems. We can read that directly from where it sits. We can bring those systems, and we can read any number of different formats that are native geospatial file formats. So whether those are GPS traces or vector data sets or satellite or drone imagery or climate data, we can read all of those data sets into the Wherobots Cloud Service. From there, you can then discover it, you can register it in your spatial catalog, you can build notebooks with it, you can automate and run jobs based on that spatial data, and then you can ultimately use that to derive and build and deliver those data products. This last bit here is something that we're working on, is being able to connect that data with AI directly. So that's something that's coming in the not too distant future. But that's what I was speaking to earlier, is being able to read and run those and use your AI agents to interact with your data that's in Wherobots as a cloud service. And then finally, push that data out on the other end. If you need it in other systems, if you want it in Snowflake or Databricks or other systems that you're working with, you can push that data out, or you can connect it directly into front-end applications that you might be working on or building with. So this is a common pattern that we see is, you want to read, you want to process, you want to analyze, you want to automate, and then you want to deliver those data products to your systems of record. There's a lot of advanced functions that we have in Wherobots as well. We'll show you today map matching with GPS traces and GPS device signals. You can also do things like geocoding and traffic isochrones. We've got the ability to deliver distributed PM tiles. So you can create PM tiles as a data product and serve those out into your tile server applications. We also have advanced functions for things like DB scan, hotspot analysis, outlier detection. So a lot of rich functions that really help you answer questions about the physical world. And then lastly, I mentioned this already, we really want to make it easy for teams to use and leverage AI in their spatial data products. So being able to take that satellite imagery, take that drone imagery, use either foundational models that are imagery agnostic, or use trained models that are specific to a certain image set. We have multiple that we support already. We've got the SAM segment anything model from Meta. We've got the ALV2 model. We'll be showing you that one actually specifically today. So if you want to ask a question like, hey, detect me all the solar panels, and turn the results into bounding boxes around those solar panels. Or if you want to do, find all the airplanes at a given AOI, you can do that as well. So you can just, ask the question. You can use a text prompt to get the results. It will run the inference on the imagery that you provide, and you get the output at the back end of it. So that was supposed to be an input to this next question, which you've already answered about how are you using, or what challenges do you have with running inference in satellite imagery? Cool. All right. So last slide for me, and then we'll jump into some demo time from Daniel. Really, when we're talking about the lakehouse for map making teams, this is the pattern that we see. So we're talking about data sources from lots of different systems, from maybe it's vehicle trips coming from GPS events. You got road graphs that you might be taking. We use Overture and OpenStreetMap, for example, within our analysis, I believe today. You maybe overhead imagery. We use NAPE in this particular analysis. You bring those raw data types into your Wherobots. You connect directly into your S3 storage. You can then register tables with those and build tables in Iceberg with those. You can run functions. You can run lots of different types of functions within Wherobots DB, are 100% compatible with our open source engine. Do all your spatial processing for make line or intersects or points. Do your map matching. Do your advanced functions, and then you can serve it back into your end user applications, whether that's other tile servers, or you want to work with it directly in, say, QGIS. That's something that we've got coming too. So lots of different ways that you can then deliver those end results into the applications that you support. All right. I've been talking too much. I'm going to give it over to Daniel to show you what we're talking about.
Awesome. Thank you so much, Ben. I'm going to get my screen shared here. Everybody see my Wherobots workbench loaded up? We're good to go? Awesome. I'm going to kind of give an overview of the platform, kind of our main interactive layer here, and then I'm going to go into our two-part demo. So our demo is going to really talk about that initial ingestion of about 10 billion GPS points, conversion, map matching, and then we'll jump into the advanced raster inference and machine learning part of this to generate some bounding boxes around some detected roads. The main interactive workloads that Wherobots supports, in addition to all of our automated workloads, are via hosted Jupyter notebooks. We have a variety of different environment sizes for you guys to choose from. GPU optimized ones for the machine learning models that we host or the ones that you folks bring. As Ben mentioned, we do support bring your own PyTorch models, so we can bring those in, run those at scale within our infrastructure, as well as these memory optimized instances as well. These are some of our larger processes that require a massive amount of data being stored within each node of the system. We also support multiple regions, so we are EU West, US West 2, and US East 1 as well. We have more regions coming online. Our spatial data catalog is available as well for our community and our pro members as well. And so we host a variety of data sources in our open and our pro data catalog. All of the Overture Maps data, each release is detected within 24 hours, same with the Foursquare Places data, and all those are available for you folks to use regularly. We support S3 storage and storage integrations as well. And so you're actually able to attach your own S3 buckets directly. So you don't have to bring your data into the system. You don't have to convert your data to our proprietary format or bring it over into our storage. You can attach directly to your S3 storage and read directly from there. Same with your Postgres database, same with other applications as well. All right. I'm going to kind of give a quick overview of the results of this first, right? So the main point of this really is to generate these updated road segments, right? So then this is that noisy GPS trajectory here. When we map match it here, we get these really nice trajectories that match our existing road network. GPS data is inherently noisy. I just spent some time yesterday kind of walking around the neighborhood, looking at my phone, kind of tracking the GPS accuracy, trying to see how accurate in an urban environment, a populated area with low buildings. And the overall accuracy was about 10 meters, right? And so like that's on the newer iPhones, like that accuracy that's built in is really not as good as it would appear when you're using these navigation devices, right? When you're driving along, it snaps you to the road dynamically, but the data that it's collecting isn't as clean as that. And we can really get a representation and see how this data kind of doesn't sit anywhere near the line. It kind of jumps on both sides in some places here. We go from the south side to the north side to the south side. And so rectifying and cleaning this data, getting it ready for not just reinforcing our existing road network, but when we don't map match these, right, we have a whole different signal of data, right? When we see GPS traces that don't map match, that don't sit on the network, that's really clear signal that our road network is out of date. So like I said, this process really is dynamic, right? We can run this in an automated job. And when you run this on this size of data, it runs in about 15 minutes for a little less than $15. Depending on the size of your data, the distribution, like these numbers can be, optimized and reduced depending on your workloads. But for this, we're going to consume about 10 billion GPS points. We convert that into about 16 million unique trips, and we filter that down to about 90,000 trips in an AOI in Central Oregon that we're going to kind of look at here in this Bend, Salem, Eugene area. So this is kind of what our overall workflow looks like. We have raw GPS data that comes in. It is transformed and loaded into our lakehouse. Those GPS points and those trips are then map matched. We end up with two sets of data. The matched trajectories, those get a unique fingerprint for ad hoc analysis. And we have these unmatched trajectories. The unmatched trajectories, together with the bounding boxes identified through foundational models, are then sent out to the editors and the data creators and the map makers to then update new segments and apply them back to our graph, to our road graph for networking, for routing, for whatever the needs are for that base map layer. So one thing that's really elegant about Sedona and about our platform is the ability to chain all of these pieces together in very straightforward statements, right? And so here we are not only consuming our raw parquet data, we're actually generating a new delivery date column here, as well as doing that spatial transformation, right? We're generating this four-dimensional point, this Z, X, Y, M, right? So X, Y, your elevation and your timestamp, are all being generated on read. That data then gets appended to the existing GPS table in our spatial catalog. And we can update the spatial index depending on our needs and depending on our workflow. Here, we use the Hilbert curve, right, a space filling curve to resort and reorganize our data on disk. This is a little bit different than your traditional like RDBMS, like GIST or B-tree type of index, in that like sorting and ordering the data allows us to do that spatial data retrieval, that spatial filter pushdown, right? Rather than say, hey, load all of the data, then filter to your AOI. Let's just read the data from our AOI first. We don't have to load it all into memory. We don't have to do full table scans looking for this. That data is sorted and able to be brought to the surface through spatial filter pushdown. We'll see that in just a moment. Like Ben had said, we support 200 different ST functions. Those are your typical spatial type, your vector-based functions, and then additional raster functions as well. Here we consume all of that GPS data, sort order it by the timestamp, and then just make our line. This is creating that original trajectory that you saw, that noisy GPS trace that will sit on either side of the line, kind of bounce around due to the inaccuracies in the collection and the variability in the accuracy of the collection there. Same kind of song and dance here. Create our table, append it, and then update our index when needed. This can be done nightly. This can be done daily, like whatever your guys' workflows need. Automating this through Airflow, automating this through our REST API really gives you the flexibility to deploy your jobs and orchestrate your analytics as needed to fit your guys' business logic. Take a quick look at some of these traces. You can see here the individual points, definitely, just stringing them together to make a line. Again, you can see we're on both sides of the line in a lot of these places here. We have inbuilt, as you see here, Kepler integration. So the Sedona Kepler integration allows you to kind of visualize and work with your map data in situ, kind of allowing you to check your analytics and check your results there. We actually, like Ben said, are able to generate PM tiles from this system as well. So if you have 90 billion points or 10 billion points and 17 million linear line strings that you would need to represent, it would be best off to generate those as PM tiles and then render those within the notebook or serve those out through any of the web viewers that can consume PM tiles directly, or you can put it behind like a lightweight tile server and render those as ZXY endpoints as well for your more traditional legacy map systems. So this is the area that we're going to filter in on. And before I jump down, I want to pause for a second. Are there any questions that we can answer real quick on this?
Yeah, we have a raised hand here. I'm going to go ahead and allow you to talk, Jordan. If you want, feel free. Go ahead. Jordan, if you got a question, I see you raise your hands. I'm allowing you to talk if you want to.
It's a rogue. All good, sir.
Rogue hand. Okay, no worries.
Awesome. Awesome. So from here, I want to highlight that spatial filter pushdown, right? So this bounding box here is the AOI that we're interested in. Those 10 billion GPS points and those 16 million trajectories that we generated cover the entire country. To just analyze this area, we need to retrieve that from storage, and we use this spatial filter pushdown. It's just a where clause, right? With this ST intersects predicate here. We actually have a whole host of different predicates like this. So ST within, ST contains. So however you guys need to kind of communicate that spatial relationship, right? Like how if it's basic topology, like I said, within, connects, contains. We support all of those types of predicates as well. So you can use all of those to retrieve the data that matches your guys' business logic here.
Hey, Dan, we got one other hand raiser here. Sanjana. So Sanjana, I'm going to allow you to talk. Go ahead. Feel free to unless it's another rogue hand. We're okay with rogue hands. That's fine too.
They're saying hi. They're saying hello. It's all good.
All right. I guess not. That's fine.
Yep. Feel free to type your message in there as well. We can get to it at the end as well. So at this point, we have read in 10 billion GPS points, converted them to line strings, stored them in our database, retrieved them for this ad hoc analysis of map matching that we're about to perform here. And when it comes to map matching, we really have two modes, right? We have this fast mode, this local fast mode, and a more advanced mode. Here we're using our local mode. This allows us to get the majority of these simple use cases kind of rectified against our existing road network, right? We end up with a set that are unmatched, and then those can be either run through the advanced map matcher, but those still, if the road network doesn't exist, like we're still going to end up with unmatched trajectories, right? But the point I want to make here is that when we perform map matching, it is a straightforward process, right? You build a map matcher, you set the search distances and some noise variables in the configuration, and then you just call matcher.match. Like that's it. You can actually bring your own matching algorithms. We support bringing your own networks as well. There's a simple schema matching that you would need to do to facilitate using your own network, but those are really simple, essentially mainly field name conversions, right? And so it's a very straightforward process. Bring your own matcher, bring your own network, and just sub them in directly for your network here, and then your geometry column here. This is that schema I was talking about. It's really just, sets of source destinations. That's really what it comes down to. So it's a really easy, really straightforward schema. It's not super complex for what you need to perform that map matching to the existing road network. Right. And again, we can kind of zoom in here. We saw some of these before, but it bears to kind of render again. So we can see a lot of these match trajectories here. All of these get written back out to our database. And then we start to detect the empty one. So our map matcher returns the observed points and then an empty string if we can't match it, right? We then take that data, because that is extremely, like I said, that is valuable signal, right? This is telling us that people are driving here, but there's no ways. This could be new driveways. This could be new subdivisions, new apartment complexes, right? All of this information is super valuable for delivery services, for navigation, for safety and navigation, for logistics and planning. Like having a complete road network, even down to the road network within an apartment complex, is extremely critical for that last mile delivery that Ben was talking about before. So in this part here, we take that data and write out those empty results. Again, ST is empty. This is one of our, binary, functions that, you can join where, use them as join predicates or use them as filtering predicates here. And so then that just gets written out. And that is, again, one of these signals that gets sent out to the map makers to go to these areas and navigate directly to them. A lot of times with map updates like this, in legacy systems and in times gone by, like you would just have to kind of reference your road network against imagery, right? And then say, oh, well, here is something that was missing. We're going to go and digitize this. But in this instance, like you are able to direct your editors to where we have seen high quality signal that we are missing data from.
Hey, Dan, we had an interesting question on the chat here. What about the overshoots, undershoots, and lines and the multi-polygons?
Yeah, so the overshoots and undershoots, like that would typically be rectified within that map matching process. I think the local map matcher, or excuse me, the advanced map matcher would be a little bit better fit when we see a lot of overshoots and undershoots. But if you check the documentation on it, it's a lot of these map matchers and the ones that we have that we've built internally are based on this kind of Markov model of like best fit kind of thing. And so that's how we kind of rectify those, and overshoots and undershoots should be accounted for in there as well. Cool. The last part of this demo is taking these matched trajectories and creating this unique fingerprint. We store these unique fingerprints with these matched trajectories so that we can do ad hoc analysis, right? Think of a delivery company going from a specific type of store to a specific apartment complex, right? Being able to say, look, this trip from, McDonald's to, wherever this imaginary business or apartment complex would be, we see this unique trip again and again and again. And by virtue of the ordered stops within the network and those unique IDs, we can kind of analyze that post hoc without having to do all of the spatial analytics on top of it, right? Doing the spatial analytics up front enables ad hoc analysis downstream at a faster pace. Again, one of our, lovely ST intersects here. This is optimizing behind the scenes. There's like, high speed optimization that goes into joining these two things together. Again, we're using those matched points and then that OMF road network that we've generated to kind of match those together there to create these trip fingerprints. I'm going to pause for a second before we jump in to the computer vision and the OWL V2 model, just for any questions or any raised hands. Even just saying hi is okay. Perfect. All right, jumping into the raster inference side of this. As Ben mentioned, and I've mentioned before, like we host several models. We have the OWL V2, we have a solar panel detection model that's built in, a classification model built in, and currently have a offshore infrastructure detection model as well. We have other ones that we're bringing on board, as well as a whole new version 2 of all of our raster inference products are on the way as well, that really combine that entire workflow of pre-processing, inference, and then post-processing as well. In this demo, we are covering, like I said, that area in Central Oregon. We're actually going to use the NAPE imagery for this. I think this was maybe a year or two ago, but it's rather high resolution, right? This is about half-foot 3-band imagery. And I think that we have about 14,000 individual tiles that we work with within this process. And the goal here is simply to extract bounding boxes around paved roads so that when we send our editors these unmatched road segments, we can send them this inferred signal as well, right? So we have this first-class signal of these roads or these trajectories that didn't match, but we have this rich set of inferred signal as well that would allow us to say, hey, if you're already in this area searching, please go to these areas additionally and maybe get ahead of the curve, right? Let's proactively add these new road segments that we've detected into our network as well. But kind of how do we actually do that? You can see here, this is all of the imagery that we actually included. So all of these individual tiles, these are actually able to be read and generated dynamically. So the NAPE imagery come in these big tiles. Subsetting that down and preparing that for modeling can be really onerous. We have a lot of inbuilt tools that just simply, when you read, you can define this tile structure here. And if you don't want to define it yourself, it'll actually read the metadata and understand that internal block sizing and try to match the metadata and then have that internal kind of subsetting in memory of the data. It bears mentioning too that this imagery is actually stored as an OutDB raster. This is one of the optimizations and benefits of using Wherobots, and rather using Sedona within Wherobots. We've added this OutDB type that allows you to really store more of a reference to your TIFF file rather than storing the uncompressed imagery within your database.
Hey, Daniel, we've got a question here. I think this is a good one from John. Do you have to explicitly call broadcast, and how do you come up with the optimal partition number?
So those are great questions. You don't have to call broadcast manually every time. And so you can like if you know that one of your data sets ahead of time is much smaller than the other one, like that would be a good indication that you would want to broadcast it. And if the system doesn't pick that up automatically, you can define and say, hey, we want you to broadcast this smaller data set out to all of the other ones, right? So that would be a good one there. Determining optimal partition size, there's actually a lot of optimization behind the scenes that goes on within Wherobots and on top of Sedona already that tries to build the optimal partitions there. Kind of a rule of thumb that I've been working with. I think there's a lots of different schools of thought on this. Kind of the way that I work with it is like about every 1,000 records, I want a partition, right? And so then you'd have about 100 for every 100,000, and like that's kind of how I approach it. This really depends on your data density. This really depends on your data distribution, and it depends on the size of your geometry too, right? If you have like doing joining against country boundaries, right? The vast majority of countries are rather small, but there's a few countries whose boundaries, like Canada, United States, Russia, China, like these boundaries are huge geometries, and those kind of need special treatment and would really break a lot of basic rules of thumbs about partitioning. Does that help answer your guys' questions? Awesome. I think that we could do, huge, internal optimizations within distributed systems are, heavily researched today, right? Like when to do specific types of partitioning, how to do them sorting as well. So there's a lot of research out there. That might be another great webinar. It's just optimizing partitions. I'm going to jump back over and kind of talk about how we run raster inference. When we deploy models, there's really like, I think three types of models: bounding box models, segmentation models, and classification models. When you have a model that has a specific type of output, one of these aforementioned three types, there is an accompanying RS function to match that. So this is a text to BBox model here, and you really just have to give it the model ID. This is a previously registered model. When you guys bring your own models in eventually, you will have a JSON spec document that is stored in S3 or in one of your storage integrations. You would specify that as the model ID. That actually points not just to the metadata that kind of drives the inputs and outputs, but it also references the model asset that would be deployed in cloud storage as well. This model simply takes a prompt, right? We have a model ID. This is for every one of our RS functions that do inference here. You would take a model ID and your raster column in our table. And then this one has the prompt and a threshold parameter as well. And so this could be, roads. This could be, any number of things that you want to kind of detect here. There's actually a rather large lexicon that Owl V2 pulls from. And so you guys can take a look at that to see kind of what word that understands best. But this is all it takes to run inference, right? On the back end of this, what we end up with is our image and then an array or a list or a struct of all of our actual detections in their confidence interval. Right. So now that we have multiple detections within imagery in a lot of cases, that gets processed in the small post-processing step where we kind of explode and divide those out into the individual records. And we can see here that we have lots of bounding boxes, their confidence score, and then the label here. Since this is essentially like a one label extraction, like there's only label value of one. Lots of models have lots of different labels that come out with it. So then you would be able to filter by the individual classification, segmentation, or whatever that result is that you were looking for, just by filtering down by the label here. Scroll down here. I think what's super great about this is now that we've worked with our raster inference, and this is something really unique to our platform, is you can work with those directly with ancillary vector data, right? So now we have run our machine learning model, generated these polygons, but now we want to locate those that fall within do not intersect with our road network, right? And so again, that joint predicate based on ST intersects here, where the current road geometry is null, right? This allows us to find all of the bounding boxes that intersect, but then drop off everything that didn't have a match. And you can see those results here, that these are some of the bounding boxes that we detected that don't intersect the existing road network that we have. And you can see some of the imagery here of the ones that we pulled out. So we're definitely seeing some really high resolution paved roads. Really nice one here. This looks like a driveway. This looks like a rather new one, kind of offshoot here. So definitely some areas that we would want to address as well. That's kind of the bulk of this demo. I'd love to answer some more questions. I think that we have a few more minutes. Ben, I'm gonna toss the mic back over to you, sir.
All right, thanks, Daniel. Yeah, so feel free to keep adding in your questions as you can stop presenting here, Daniel, so I can share my screen. All right, there we go. All right, so we're going to do a real quick wrap up with just a quick case study. This is from the Amazon Last Mile team. They prepared this for the AWS reInvent this past year, so we're sharing that since they made it all ready for public consumption. And so just so you know, the Last Mile team at Amazon, these are the people that figure out how to best deliver your packages to your front door, are heavy users of Apache Sedona. I've been using it for a long time, and a number of other open source systems to do their map making and deliver their digital representation of the physical world that ultimately is used in Amazon trucks for their drivers as they're driving your packages that you probably bought from them around. So what do? They take satellite imagery, they take aerial imagery, they take deep GPS traces, just take street side imagery and the on-road collection from edge devices. They conflate all those things into a neural network and use computer vision and a knowledge graph to go about maintaining and updating their very detailed representation of the physical world. And what they start with is this sort of incomplete geospatial data set. And what they are maintaining now is a very complete, very detailed spatial data set so that they can enable their drivers to successfully navigate to your home and also take into consideration the packing of the truck. So, for example, they run bin packing algorithms where they actually look at how they should pack the truck from back to front to where the back of the truck is to where the driver is, and figure out what the best location to put each package in the truck is. So, for example, if you're in San Francisco, if you're driving around and there's a Giants game at the what is it, Oracle Park now? Sorry, it changes every few years. um, they'll answer that and enable that driver to move and navigate around that traffic while it's happening, not have to deliver packages at that point in time, deliver them later when the game's over before it started. And so ultimately, this is the outcome that they're solving for, and this is something that's kind of been an evolution for them. But they take these sort of rougher representations of the physical world, and they add all this additional context, additional information, where the location of a community center or mailroom is, or something related to a particular place, where there's road construction going on, where there's stop signs, other information. Maybe there's a wreck that's happened. All of that is taken into account and their representation of the physical world that's then used by their drivers to best navigate getting those packages to your house. So I think that's a pretty cool case study example. Okay, I think we've got one last question, and this is really a question that our folks here wanted to hear from everybody. So if you would like us to follow up with you, we would love for you to tell us. So this is for our team members internally. If you are interested in what you've learned about today, just let us know. We won't bug you if you don't want us to hear, you want to hear from us, but if you do want to hear from us, just let us know and we'd be happy to follow up. I'll just give that a minute to run. Cool. Thanks, everybody. Got 18 of you, so just give it one or two more minutes. If you want us to follow up after this, just let us know, and we'd be happy to do so. I'll actually do this as a QR code too. So if there's folks that are not on the Zoom, if you're on LinkedIn or another system, YouTube, and you can tell us here as well. Just let us know if you want us to follow up with you. Cool. All right. So while we're finishing that up, why don't we go back to the presentation, share, and I'll go ahead and end that poll. I think we've got a good number of responses. Thank you, everybody, for sharing your, whoops, I hit the wrong button. Darn. All right, slideshow. Okay. Okay, so let's do some final Q&A. Happy to answer any questions that you all might have. Feel free to raise your hand, or if you have questions, I'm happy to unmute folks if you want to talk to us. We got some good questions already from the folks in the chat. Daniel, one thing, there's a few questions that come up here pretty consistently. What are some of the ones that you think are kind of most tricky when you've done this demo?
I think questions about like how the model behaves and what it does like under the scenes, right? Like these are super advanced models that like a lot of ones are can be difficult to kind of understand behind the scenes. But I think the some of the tricky ones that are how can I get started and how can I start using this, right? Like it seems like a rather straightforward question, and it really is in a lot of ways. But I think that we really rely on high quality individuals and data to kind of feed into these systems, right? And so we actually have a lot of ability to do data cleaning and data pre-processing steps as well. Like a lot of these demos, like you kind of put your best foot forward in a lot of ways, right? But the generation of this graph network, right? Like we build that internally, and we have all of the tools that allow you to take like messy or unstandardized road networks and convert them into something that's well structured to meet map matching, to work with other platforms as well. I think that, additionally, like trying to communicate the ease at which you can work with all of these different tools in one place. Like there's not a lot of ways that you can go from doing this type of vector analysis directly into machine learning, directly into additional, like downstream vector analysis, right? Like doing that filtering of those bounding box results all within a single notebook. It's one of those where it seems like it's like, no, that doesn't seem right. Like, how can you do this all within one? But the platform that we've built really allows you to switch between these different models and these different modeling environments really seamlessly. Like you can really do it all within the one platform.
We got one question while you were talking, Daniel, from Violetta. She asks, do you plan to integrate with Esri ArcGIS Pro software?
Right. So right now you actually can. So there's a few ways that you can do this. ArcGIS just released, I think it's still in beta, their Parquet reader, so their Geo Parquet reader. So when you read in this data and you generate an analysis like this, right, writing it back out to a Parquet file or even GeoJSON, right? Like the export formats that we can write to are directly readable in ArcGIS, in the latest versions of QGIS, those other platforms. Additionally, using PM tiles, right? The generating the data in PM tiles using something like the tile server GL, or I think it's the Martin or the Marlin server, allows you to host these data as the ZXY endpoint that Esri, that QGIS can directly consume, as well as serving this data to like the JavaScript API from Esri, right? Using that intermediate tile server, you can actually make a vector tile layer with the Esri platform, like I said, the JavaScript API, and pull all of this large scale data in and render it and work with it like any other vector data source. We're actually working on a custom GIS layer, a custom ArcGIS, a custom JavaScript API for ArcGIS layer that would allow you to do this without the need of an intermediate tile server. So there's lots of ways to work with it, either from format conversions, hosting it through tile servers, or even custom layers as well.
Cool. Alrighty. Well, I think we've hit a lot of things today. So just to close out for folks, thank you for those who shared that you want us to follow up. We'll definitely do so. Just also as a reminder, like I mentioned, Wherobots is 100% built on AWS today, so you can, if you want to try out our Pro tier and get access to all the advanced functions that we walked through and talked through today, things like map matching and their inference, those are available on our Pro tier, so you can get started with those on the AWS Marketplace. You can also, we're going to be sharing out after this a follow-up, another one of these in about a month. We're going to be really digging into a telco use case. So if you're interested in telecommunications and understanding how to manage telco networks and optimize those networks, so we'll be talking about that next month. And then if you want to reach out to us directly, we also have a contact us sort of button on our site. So please reach out there, or you can email me, ben@wherobots.com, Daniel@wherobots.com is our email addresses. So I want to thank you all for joining. Really can participate or appreciate your participation and your interactions. This was really awesome. And we really thank you for your time today.
Cheers. Thank
Awesome.
you.
Thanks, everybody. Have a great one.